Y'all ready for math? Y'all ready for math? All right, it's Mr. Berto back again with another virtual lesson. I'm going to teach you a lesson. Let's rock and roll, continue with our integration here. So what is this, Friday? Okay, you guys got 1 week left until AP exams. So you'll be having, I think, Friday of next week to work on the take-home assignment for this chapter. And I'm kind of setting it up, hopefully, so that the next 2 weeks after that for APs, we only just do a little bit of review work in here, so kind of take it easy on you. As long as you promise me, after those 2 weeks, we rock and roll, come back into a chapter, and then we'll see how much time we have left, how many things we can get into. So we'll kind of just take it as it comes. So hopefully you tried the homework. Basic integration, you should really be a master at this point in time, which is really, when you want to integrate a function whose argument is only one single letter. So here it's only a squared. It's not like a plus 6 quantity squared, okay? It's not the square root of, the sine of a minus 6a, something like that. We'll talk about stuff like that today, but make sure you know how to rewrite. Okay, there's really only one, basic integration rule that we know so far. What's that word? Starts with R? Recall. Okay, and that's if you actually want to take the integral of one single letter raised to a numerical power. And don't forget to put that little du on the end. We're going to take u, rewrite that base, add 1 to the exponent, divide by that number. Don't forget to add some cookies. Hey, some cookies. And, then we're going to indicate that n can equal -1. Not that you need to worry so much about that, but we'll speak more about that Tuesday of next week, something like that. This list will grow, but it won't grow today, okay? The idea is that, going back to the homework, as long as you got one single letter raised to numerical power, you might want to rewrite things that way, then it should be pretty easy to integrate. And make sure you can simplify afterward, okay? So you really should be a master of basic integration at this point in time. This one bothers people. You have functions connected by multiplication. You cannot integrate over multiplication. You could use something known as integration by parts for this, but we don't talk about that. That's a BC topic, so if you're taking BC, we'll speak about it next year. I don't know, maybe if we have time at the end of the year, we'll talk about it a little bit just to get you guys prepped. We'll see what's going to happen. Anyway, there's only one thing in AP Calculus AB and in this class that you need to worry about if you can't integrate, right? If you have things that are not set up in basic integration form, which right now is one single letter raised to numerical power. There are other types as well that we'll speak about on Monday. But if you don't have stuff in form to basically integrate, you could either use something known as integration by substitution, which we're going to talk about today. It's the only rule you need to worry about in Calculus AB. Or you could perform some kind of algebraic technique to force something to be in a pleasurable form to integrate. And you can see this is just t to the first times t to the 1/2. This is just t to the 3/2. We've now made it a u to the n type of situation. So it should be easy to integrate, okay? So, the first thing you should be thinking is, can I perform some kind of advanced algebraic technique here? Or maybe not really advanced algebraic technique, just an algebraic technique. And you'll see that you can turn it into basic integration. That could happen over here with this little example. The integral of x plus 2 quantity squared with respect to x. Right now, the best way for you to integrate something like this would be to double bubble it, right? Make it x plus 2 times the quantity x plus 2. Then you do your double distribution. Then you set up a nice little basic integration situation. There are ways that could be avoided, okay? And that's what we're really talking about today. The reason we have it u to the n power, we know that n is a constant. This u doesn't need to be one single letter, okay? It might not just be an x, raised to the second power. It might be a quantity x plus 2 raised to the second power. Or maybe it's cosine x plus, 3e to the 2x, quantity to the second power. So basically, what if, the u is not one single letter, okay? What if u is not one single letter? Oh no, Mr. Berto, what do we do? Well, let's talk about it, okay? What we can actually do is we can force it to be one single letter, okay? But we'll talk about that in a second. Over here, some people just try to treat this like it's one single letter. They're like, you know what? This is like, my u right here. Instead of saying x plus 2 quantity squared, I'll kind of think about it as u squared. And then if you want to integrate, something squared, one single letter, you rewrite that one single letter, but we'll rewrite the u this time. Add 1 to the exponent, divide by that number, add c. And this is actually correct, believe it or not. Okay, and some people are like, well, how do I know if it's correct? Well, you can check it. Check to check it out, okay? And you can actually take the derivative with respect to x of our answer right here, because remember, that's somebody's derivative in there. Whose derivative? The answer's derivative, okay? I'll write him as 1/3 x plus 2 quantity cubed plus c. Let's take a derivative, right? We're taking the derivative of a function here. As argument is not one single x. Chain, roo. Drop that 3 down. 3 times the third is 1. Rewrite the inside, the entire x plus 2, raise it to the 1 less. That'd be the second power. Multiply by the derivative of the inside. The derivative of x plus 2 is 1. And then add the derivative of c, which we know is 0. And this is just a really complicated way to write our integrand. Okay, so apparently this was successful. I talked about this last lesson. The only way that this is successful is because the derivative of my u is equal to 1. Okay, that doesn't happen down here when you have 2x plus 3 quantity cubed. Okay, this u right here, if you kind of think about the 2x plus 3 like it's one single letter, the derivative is not 1. We know the derivative would be equal to 2, right? And that's going to cause this to fail. If you try to be like, you know what, I'll just rewrite the u, add 1 to the exponent. 3 plus 1 is equal to 3. Real good, Berto. Sorry, early in the morning video today. Not that I'm not normally used to teaching this stuff first period anyway. But, add 1 to the exponent, divide by that number, add some cookies, put a not equal to sign here. Okay, this is actually not correct. And if you want to check to show why it's not a correcta, well, let's actually take the derivative with respect to x of our answer, what we think is the answer. I'll write 1/4, 2x plus 3, quantity to the 4th, plus some cookies, equal to, drop the 4 down like it's hot. 4 times the 4th is 1. Rewrite the inside, raise it to the 1 less. And here's where the trouble begins, okay? Now you multiply by the derivative of the inside, which is equal to 2. Then add the derivative of c, which is 0. And we end up with 2 times the quantity, 2x plus 3 cubed, okay? And we know that that is not our original integrand right there. It's really the 2. How do you get rid of that 2? Because if we got rid of that 2, then we have the integrand. Well, multiplying by 2 to cancel it out, you would divide by 2. And that's the real thing with integration by substitution that we're going to talk about. Remember, integration is anti-differentiation. Integration by substitution, it's kind of like chain rule for integrals. Remember, chain rule for derivatives, you have to multiply by the derivative of the inside. Chain rule for integrals, which is really kind of u substitution, you divide by the derivative of the inside, but you also divide by the derivative of the inside before the integration even takes place. So you should follow the process we're about to talk about. If you try to do these problems in your head, it can be very, very dangerous, okay? They call that mental integration or integration by observation. Look, when you get good, you could do stuff like that, okay? But there'll be some people taking AP Calculus who still won't be able to handle integration by observation, which is fine. It can be very dangerous. It's easy to make silly mistakes, and it really doesn't save you all that much time. It's helpful in certain situations, don't get me wrong. But if you want to take Calculus AB, you don't really need to worry about integrating mentally. BC is a little bit of a different story because it speeds things up a lot if you integrate mentally, so it is quite useful, but we're really getting ahead of ourselves here, okay? The idea was, what if u is not one single letter? Over here, besides, doing this and getting lucky because the derivative is 1, you could have double bubbled this thing. Over here, right now, you're like, hey, how am I supposed to do this? I'm getting the wrong answer. You could triple bubble it, which we know is extremely annoying, okay? And then you're going to get an answer that you might actually not know is equivalent to an answer they might give you in multiple choice, okay? So if you want to integrate a function and the argument is not one single letter, we're going to force it to be one single letter. Force it to be one single letter. So we're going to make like a Jedi and force this thing to be one single letter. And people are like, what the heck is that? What's going on? Well, let's dive in and do an example before we write down the topic sentience. And the example is number 1. Okay, let's talk about another way to do it. So basically, if you want to integrate this thing, remember, if you have a variable raised to a numerical power, you want to use that u to the n rule. The problem is, this is not u, this is x plus 2 right now. But we're actually going to not just treat it like it's u, we're going to set it equal to u. Okay, over here, I'm going to write u equals x plus 2. And what's really going to happen is I'm going to perform a substitution. This is a substitution, substituting something with its equal. So basically, I'm going to take out that x plus 2, replace it with a u. Now I have u squared dx, and I want to integrate that. And some people are like, oh, wow, this is easy. Now it's easy to integrate this. Hold on a second there, Poppy. This is the integral of u squared with respect to x. You can't integrate u with respect to x, okay? This doesn't need to be a dx over here. This needs to be a U. And some people are like, well, but how the heck am I supposed to get that that's a du over there? Well, believe it or not, we have u equal to x plus 2 here. How do you turn a u into a du? People are like, I don't know how to turn a u into a du. Well, how about this? How about we did some old school problem, back in the day when we first started calculus, we had y was equal to, I don't know, maybe sine x or something like that. And I asked you for dy over dx. And to get dy over dx, we know we just take the derivative, okay? And the derivative of sine x is equal to, you all better know that in a world of derivatives, sine is the good guy, okay? So cosine x right there. The next lesson, he's going to be the bad guy because it's going to be integrals. We'll get there soon. But notice how we had a y. Suddenly it became a dy over dx when we differentiated both sides with respect to x. So if you actually want to get a du and you start with a u, differentiate both sides, okay? I'll take the derivative with respect to x of both sides. Just remember, you're not going to get a dy over dx here. You're going to get a du over dx, right? The derivative of u with respect to x is equal to, and the derivative of x plus 1 with respect to x is just equal to 1. And gee willikers, Batman, we now have an equation that has a du in it. And that's what I want. I want a du over here. Not only does it have a du as a variable, it also has a dx. And that's what I want to substitute for. So here's a relationship between du and dx. Let's cross multiply. Okay, du times 1 is du. dx times 1 is dx. You're able to treat the du and the dx like they're variables because they're representations for one single number. The difference of the u values, the difference of the x values. It's just a difference. It's just subtraction. And here you'll see that du is equal to dx. So besides performing the first substitution to take the x plus 2 and make it into a u, now you actually perform a second substitution. These guys are connected by multiplication. Take out the dx, replace it with a du. And it appears that we now have what's known as an equivalent integral. Kind of. Technically, you need bounds for it to be an equivalent integral. You don't know what the bounds are. We'll start putting numbers here and here after AP exams. But what you have now is an integral that you can do, okay? This is in u to the n form. One single letter raised to numerical power. People freak out. They're like, well, shouldn't it be like x squared? No, we want it to be u squared because we have a du over here. And we know how to integrate u squared, rewrite u, add 1 to the exponent, divide by that number. Don't forget to add some crustaceans right there. Partial lobster myself, but crab is good as well. Just don't circle this as the final problem because they showed you an integral in terms of x. You can't give an answer back in terms of u. That last step, you want to say, you know what? U is equal to x plus 2. Let's bring that back and plug that in over here and end up with x plus 2 quantity cubed over 3 plus c, and we know that's the correct answer, okay, because we actually differentiated it before to actually check to see if we got the correct answer back, and we did, okay, and this right here is actually known as integration by substitution. Megastar! Integration by substitution, by substitution. I'm going to change, I'm not teaching math next year, I'm going to be teaching, music, okay, specifically singing and chorus. Sorry, Miss Nagel, but maybe she can come in and teach BC calculus. Integration by substitution, and a lot of people actually call this U substitution. Substitutione. Okay, and the reason they call it U substitution is U is the most popular letter to represent a function of X, but it doesn't need to be U, okay? I've had kids in the past use swirly substitution. Some kid decided to use swirly instead of U, and then you have swirly squared times D swirly. Look, if you could do stuff like that, you better be good, okay, before you start messing around that way. But really, you could use any variable that you want. Integration by substitution, and this is where we force, little star, start. We're going to force a basic rule. I'm really messing up today. Like there's no spacing in between there. Suddenly it's capital R for some reason. What's happening? I don't know. All right, so we're going to force a basic rule, and that's what we did. We took something that was not basic integration because the argument was not one single letter here, and we forced it to be basic integration. And this is actually extremely mechanical, believe it or not. You'll get good at this, okay, if you practice it. If you don't practice, you're done, okay? That's the way integration is. You have to practice it. Look, you might be like, yeah, but derivatives are easy. Integrals are a different animal. I'm telling you, man, or woman, or whatever. So make sure you practice these things right here. You will get good at these, and eventually you get so good at integration by substitution, you'll think every problem has to be integration by substitution, and then you'll forget how to do basic integration, okay? So we'll get back and we'll cover that, toward the end of the chapter. Let's do that other problem, right? Because this one, because the derivative inside was equal to 1, it was easy to actually, integrate anyway by just pretending the x plus 2 was one single letter. But that didn't work in this problem right here, okay? So in this problem right here, you really need U substitution, unless you want to triple bubble this thing. You could, but what if the exponent was like a 58? You can still do that with 58 bubbles, distribute, you get 59 terms. Extremely annoying. I wish it was one single letter raised to the third power, just U raised to the third power. You can make your dreams come true using U. Let's have U equal to 2x plus 3. And what we're going to do is we're actually going to perform our first substitution. Okay, now I have U to the third power, but then I have times dx. And this is an issue. You can't integrate U with respect to x. You can only integrate x with respect to x. I often go to the supermarket, I'll be standing behind somebody online, I'll just like poke them on the shoulder, they'll turn around and look at me and I'm like, you can't integrate U with respect to X, what are you, crazy? And then usually I just like end up running the other way, but it's cool to perform these social experiments in supermarkets. I don't really suggest it actually because people can get a little crazy. Anyway, so over here, I need to perform that second substitution. Not only do I need to substitute out for my, U, I need to substitute out the dx as well. And the way we do that is we take this little equation over here, take the derivative of both sides with respect to x. In this case, the derivative of U with respect to x is du over dx, obviously, but the derivative of 2x plus 3 with respect to x is equal to 2. There's a little trick to this too that we're going to use, in the next problem to show you it could be a little bit easier. But right now it's still easy, right? Cross multiply, okay? I always do the du first. Du times 1 is du. And that's equal to dx times 2, which is 2dx. Just be careful. You want to solve for dx, so I can take the dx out and replace it with something that has to do with the du. So we're almost there. Divide by 2 on both sides, and you'll get that du over 2 is equal to dx, okay? So if I perform my second substitution, we get the integral of u cubed times, take out the dx, replace it with a du over 2. Some people are like, oh, great. What do I do with this? This is weird. What's this 2 down here? That's not even a 2. That's a 1/2, right? In fact, that's a constant of 1/2 connected by multiplication. Oh, a constant connected by multiplication. You can pull them to the side. In fact, when you pull that 1/2 to the side, you end up pulling them out of the integral sign. Bring them out, bring them out. We get 1/2 integral of u to the third with respect to u, and that right there is the same as my original integral, but now in terms of u, okay? So now I actually have put it in a form where I can integrate. I can integrate u cubed with respect to u. What about the 1/2? Good question, Kermit. I'll just read the 1/2 to the side, okay? And now I'll actually integrate u to the third with respect to u, add 1 to the exponent, u to the 4th, divide by that number, add some cookies, and it looks like now we end up with what? 1/8 u to the 4th plus c. But you can't take a function in terms of x and then give us back an integral in terms of u. That last step is to do the final substitution. 1/8, let's resubstitute for u. Bring them back. The 2x plus 3, now he's quantity to the 4th plus c. And this right here, that's my answer, okay? And if you aren't convinced that's my answer, remember before, we had almost the same thing, only with a 1/4 in front. So when we took the derivative, we had an issue because this 2 is generated upstairs. But now with an 8 downstairs, the 2 will actually cancel out, okay? If you don't believe me, let's get a little check action going. Check! Check, please. Okay, let's do the derivative with respect to x of this thing, 1/8. 2x plus 3, quantity to the 4th plus c. Drop the 4 down like it's hot, but 4 times 8 is now 4/8. Rewrite the 2x plus 3, raise it to the 1 less, multiply by the derivative of the inside, which is 2. Add the derivative c, which is going to be 0 over there. And this 4/8 is kind of silly because we know that's really 1/2, right? And now you'll notice, oh, this 2 downstairs cancels with the 2 upstairs, thus leaving us with the integrand. May I present 2x plus 3 quantity cubed? So I know I did the problem the right way. Technically, what's really happening is you're dividing by the derivative of the inside, right? There's where that 2 is. You're bringing it downstairs. But you divide by the derivative of the inside before the integration even takes place. Don't mentally integrate yet. Even if you're good, try to stay away from it. Get used to mechanics. Because sometimes the mental integration is going to be too difficult. You got to be good at mechanics anyway. That's integration by u substitution, okay? You want to sub out for the u. You also want to sub out for the du, okay? You want to bring a du in. You want to get rid of the dx. So it's funny, they call it u substitution, but I think they should really call it 2 substitution because you really substitute out 2 things. I made that up. And there's another little trick you could do. Let's jump into number 3 over here, another little example. And you got to first think to yourself, is it a u substitution situation, or really even better, is it a basic integration situation? Are you trying to integrate a function whose argument is one single x? You're not here. The outside function is radical x, but we don't have an x inside there for the argument. We have a 3x minus 5. If it was radical x, it'd be easy to take the integral. You just write it as x to the 1/2. Here we'll write it as 3x minus 5, quantity to the 1/2. With respect to x, but you could see that right there, that's not one single letter. Let's force him to be one single letter and set him equal to u. To who? To u. And get u equals 3x minus 5. And there's a cute little trick you could do here. Instead of having to take the derivative of both sides, okay, believe it or not, what really happens is over here we had u equal to x plus 2, and we ended up with du is equal to dx. What really happens is you always end up with du divided by the derivative of u is equal to dx. The derivative of u here was equal to 1, so that's why I got du over 1 is equal to dx. Same thing as du equal to dx. It's a bad example to look at because du is equal to dx. Let's look at this one. You could start right here at u equals 2x plus 3 and immediately go to du over the derivative of u is equal to dx, because you could see the derivative of u is equal to 2. So what am I really talking about? The second you got this set up, you don't have to say du over dx is equal to 3. You can go right to du over the derivative of u, which we know is equal to 3, is equal to dx. It's going to work every time, and it's going to save you some time, okay? And time is money, folks, okay? So you want to be using these tricks right here. Now I'll perform my two substitutions and make it the integral of u to the 1/2 times take out the dx, replace them with a du over 3. And now look, just clean it up a little bit. That right there, it's not a 3, it's a 1/3, okay? It's a constant connected by multiplication. You could bring them to the side, bring them out, okay? And if I do bring them to the side, I end up with now 1/3 times the integral of u to the 1/2 with respect to u. And I've now forced a basic rule, okay? It's in u to the n form. Just bring the 1/3 over, connect by multiplication, integrate u to the 1/2, add 1 to 1/2. We know that's equal to 3/2. We know Claffey's divided by 3/2. Rest of us multiply by 2/3. Don't forget to add some cookies. Girl Scout cookies? Yes. Tag-alongs? Yes. Okay, anyway, now we know this is what? 2/9. But don't write u to the 3/2. You got to perform that final substitution, put a 3x minus 5, raise him to the 3/2, add some cookies, man, some cookies, some crustaceans, hopefully not your average, even though C is supposed to be just an average grade, but the world has changed, children. That's all I have to say about that. Anyway, some people are like, you know what, Berto, let's take the derivative to check our work. Sure, go ahead, but it's going to start to become counterproductive and time-consuming, okay? You'll get more and more complicated answers. Taking the derivatives will be more complicated. You can make a mistake taking the derivative, then suddenly think that you don't know how to integrate, okay? And that's not the deal, all right? So be careful. Just work on these things. You could really make them into a process. Let's do some more problems. These problems right here. Let's do number 4 together. Well, even so, all these, you could write number 4, you could write number 5, you could write number 6, you could try them right now. There is one little extra caveat here. Number 4 is a little bit different from the other problems that we did. Is it a basic integration situation? There's two reasons it's not a basic integration situation here. One of those reasons is that you don't have one single letter raised to numerical power, okay? 3x cubed plus 5 is not one single letter. The other reason is you have an x cubed connected by multiplication. If this was the first power, you could distribute did I say x cubed? X squared connected by multiplication. If this was a power of 1 right here, you could distribute the x squared inside there. Then you could easily make it into a basic integration situation. That can't happen here, though. If you wanted to distribute, you need to make 4 bubbles first, then distribute into one of the bubbles, and that would be an issue because then you'd have lots of multiplication. The good thing is if it's AP Calculus AB, there's only one integration technique you learn, and that's U substitution. So if you can't perform some kind of algebraic, manipulation to get something in basic integration form, pick a U, okay? And look, there's a list that we'll start talking about next lesson of possibilities for U, but one of the most popular possibilities is the base of a numerical exponent. If you see the base of a numerical exponent is not one single letter, try to set that equal to u. Just the base, not the exponent. I want to turn this into u to the 4th. I don't want to take this whole thing and just make it u, okay? So don't put an exponent of 4 over here. Hey, sometimes you do that. There are all kinds of weird types of integrals, but usually it's the base of a numerical exponent. You know why? Because right here, you can see my u is the base of a numerical exponent. So always try for that first. And then remember the trick over here. We have du over the derivative of u, which is what? 9x squared, is going to be equal to dx. Okay, so you can do that little trick right there. And now let's perform our 2 substitution. And the problem with that is the x squared, he doesn't go anywhere. He's still there, but not for long, because something's going to happen to him. Take out the 3x cubed plus 5, replace it with u, still raised to the 4th, and we like that. We want that exponent to be there, usually. Usually. Take out the dx, replace it with du over 9x squared. And before you start freaking out, oh, things are so complicated, we're integrating with respect to u, and there were x's present. There are x's present. Don't freak out, okay, because these x's, they're going to go away. They cancel out. That x squared that you didn't like when you first looked at the problem, you're like, this looks so ugly. That's necessary to be there, because when you take the derivative of the inside, it generates an x squared downstairs to cancel with the x squared upstairs. If the derivative of the inside was not something with an x squared in it, maybe it was just, just 9 or something like that, then this x squared wouldn't be here to cancel with that x squared. You actually wouldn't be able to integrate this thing using this type of technique. In that case, integration by parts would do. But anyway, so that can happen, and you kind of want to think about that. When I take the derivative of the inside, it's going to generate a 9x squared downstairs. The x squareds will cancel out. Now, look what happens here. You still got that 9. It's not even a 9, right? It's a 1/9. Bring them out. Bring them out. 1/9 times the integral. What's left? U to the 4th du. Okay, there's no more x's. As I like to say, it's all u. Get it? Anyway, so don't be so freaked out. A lot of times a variable will be generated in the derivative and it can cancel out upstairs. That didn't happen in the previous problems. Okay, there was no variable generated down there, just a constant. Those are actually a lot easier to mentally integrate. So if you want to mentally integrate this, you got to think about dividing by the derivative of the inside before the integration even takes place. It gets a bit complicated. Anyway, now let's integrate. 1/9 times, don't forget when you integrate, you drop that integral sign, u to the 5th over 5. Plus cookies. Cookies. Okay, and here we end up with 1/45. Take out that u, replace it with a 3x cubed plus 5, quantity to the 5th, plus c. And whoop, there it is. Whoop, there it is. Come on now. Whoop, there it is. Okay, so look, not really so bad. It's more of a process than you might think. Number 5, try it, okay, on your own. Pause the video. We're back, okay, and here's another situation where people are like, well, what do I do here? Well, first off, is it basic integration? No, for Schlugen way, okay? You got multiplication going on here that can't be rectified by distributing or really any type of algebraic technique. You have a base of a numerical exponent not being one single letter. You might not believe me, but you should. X squared plus 4 is really being raised to the 1/2 power here. And now, look, if you can't do some kind of algebraic technique to make it basic integration, we're going to force it to be basic integration. Let's pick a u. Once again, one of the most famous u's, base of a numerical exponent. And notice du over the derivative of u is going to be equal to dx. The derivative of u here is what? Twix, okay, the only candy bar with the Cookie Crunch. I miss class, children. Okay, here we have the integral. Now, look, that 2x, he's still there, but not for long, okay? Because there's a 2x generated downstairs. This now becomes u to the 1/2. Take out the dx, replace it with a du over 2x. And now we can see before we integrate, the 2x's cancel out, the whole thing. And now we're just left with the integral of u to the 1/2 with respect to u. You don't need to write that, okay? Remember, you want to start skipping some steps here where you feel comfortable, because you always want to save time on the AP exam. So if you want to integrate u to the 1/2 with respect to u, just rewrite the u, drop the integral sign, add 1 to the exponent, okay? You could divide by 3/2 if you're Rourke, but the rest of us multiplying by 2/3. Add some crustaceans, and don't forget that final step. They gave you a problem in terms of x. You got to give them an answer in terms of x. You can see taking the derivative here, a little bit more complicated as far as the chain rule is concerned. If you get good at your u substitution, you don't have to worry about stuff like that to check your work. But you can right now if you want to, if you have the time. 6 is the one last problem that we'll do. It bothers people a lot. This x right here is connected to the dx by multiplication. What you should always do is sometimes that dx kind of meanders into the problem. You could always pull that dx to the right-hand side, or that d whatever. It might be like a dt or a dy, depending on what variable we're integrating with respect to. Don't let it bother you, okay? Remember, this is really dx over 1, right? If you multiply across the top, multiply across the bottom, you'll get back what we started with. So never let that d whatever bother you. Just pull it to the side. And this is different here. Here we're integrating a quotient. There's division going on. We don't know how to integrate over division, okay? If you do need to integrate a quotient, there's a technique we'll speak about next week, but it really only works when the bottom's raised to the first power, which is not true here. Let's do this. This doesn't need to be a quotient. You could bring the bottom up. You know, the x is already upstairs. Let's bring up the 3x squared plus 1, but now we know he's raised to the -3 power, and now we have the dx. And now it's easy to see what's going on here. You know, it looks a lot like this situation here. We can see we have multiplication over here. Okay, we can't integrate over multiplication, so that means it's not basic integration. Also, you got one single letter, something that's not one single letter, pardon me, raised to numerical exponent. So let's pick a u. I think the only viable u here would be 3x squared plus 1. Sometimes you don't know what u is going to be. You just got to pick a u and go with it. And sometimes it doesn't work, okay? These are more simple types of problems. It's pretty easy to pick a u here. What else would you set u equal to? You know, the base of a numerical exponent. Some people are like, well, x is the base of a numerical exponent. That's true, but you never set u equal to x. The whole purpose of u substitution is to take something that's not one single letter and force it to be one single letter. See, x is already one single letter. You never set u equal to x. You never set u equal to one single letter. You set u equal to something that's not one single letter. Not. Remember, du over the derivative of u is equal to dx. So in this case, the derivative of u is what? What you want to grow up to be? 6s. You know, and it's funny, because they call it u substitution. They should really call it 2 substitution, because we do 2 substitutions here. We don't substitute out the x, but his days are numbered. We substitute out 3x squared plus 1, make him a u. He's raised to -3. You should always still have that exponent. Don't include that exponent in the u. It's going to flub things up. Take out the dx, and now that's our second substitution. Replace him with du over 6x. And the variables always need to match up here. Those x's must cancel out. You can't integrate x with respect to u. The 6 we're not worried about because it's a constant. It's not even a 6. It's a 1/6. And when you pull it to the side, you're left with the integral of u to the -3 with respect to u. And I can dive in and integrate that. U to the add 1 to the exponent, divide by that number, add some cookies. Don't be saying -3 plus 1 is -4. 'Tis not true. Okay, and this right here, you know, start skipping some steps. We know this becomes what? -1/12. And then take out the u right there. Replace it with the 3x squared plus 1, quantity of the -2 plus c. But probably a better way to write this is to get rid of that negative exponent. Leave the -1 upstairs. The 12 is downstairs. Now the 3x squared plus 1 is going to join him. Now raised to the +2 power. Can you see any of that? There we go. Okay, so look, lots of different ways to write it up. This is not wrong, okay? It's just that, you know, they'll usually get rid of a negative exponent, multiple choice. Not always, okay? You know, so many different ways. I mean, even this one over here, you know, you could have written it as 3x cubed plus 5, quantity to the 5th over 45 plus c. So just be on the lookout for stuff like that. And you should know that. We always talk about, you know, algebraically manipulating expressions to see what they're equivalent to. That's u substitution. It's not as bad as you might think. It's very mechanical. Just practice it, and you will get very good at it. Okay, and eventually you'll forget how to do basic integration. But we'll get back to that even in Monday's lesson, okay? So Berto signing off. That's u substitution, force a basic rule, and we'll see you all on Monday. Have a pleasant weekend. Do the homework. Don't be a slacker. You all better be doing your work. You want to take AP Calculus AB next year, or BC, the mother load, you better know what you're doing. If you want to take BC and you're not reading it, watching these videos and doing your work, don't bother, okay? Even AB, don't bother if you're not doing your work. Hey, if you got other things going on, I understand that, okay? But if you're just like, well, you know, I just don't want to do anything. No. All right, in BC, we're going to rock and roll with these things so quickly. We're going to integrate mentally because we really need to save time. Put in your work, people, is what I'm trying to say. Even if you're not going to take AP Calculus next year, okay? You know, honors calculus in college, you'll see stuff like this, okay? Remember, you may have signed up for AP Calculus already. Think about the things that we're doing as we go through these topics. You know, you might be getting good grades, but these are take-home tests. Imagine taking these tests in more of a time type of situation. Even so, I've been shortening them and things like that. So look, just be on the ball for next year, okay? Can't wait to see all you guys again. And this is Berto signing out. Stay healthy, stay safe. Adios.